Hi folks, welcome to the Math 611B Concept Roundup for sections 8.2 and 7.1. We're looking at area in the plane and integration by substitution here. As always, you can check the video description and you'll find a downloadable copy of the notes, as well as some practice material with worked solutions. Let's dive in. Area in the plane. We're looking here at area between two curves over some interval AB. So let's draw that. Let's say this is A, this is B, and I've got some curve f of x that lies on top of some other curve, g of x, that looks different. And what I'm wondering here is, what is this area that is bounded on top by f, on bottom by g, on the left by a, and on the right by b? And the answer to that question is, well, if you found the integral of f, then that would give you the whole area under f. If you found the area under g, that would give you the whole area under g. And then the difference between them would be that black area right here. So the area between these two curves over the interval AB is this. The integral from a to b of f minus the integral from a to b of g. And because of our integration rules, we can put those together into a single integral. So we have the integral from a to b of f minus g. And that's a good definition. But let's put it in the simplest possible terms. The area is the integral from the left bound to the right bound of the whatever's on top curve minus the whatever's on bottom curve. And that is going to work out for us all the time. And it actually doesn't matter whether the curves are above or below the x-axis. This algebraically is going to work out. It'll give us the area. If you do one of these questions and you get a negative answer, that means you've done something wrong. The answer, if we set it up properly like this, will always be a positive number. And we're assuming there are no points of intersection in between a and b, and that they don't switch roles. The f doesn't turn into the bottom curve at any point. So we have to have f above g on the whole interval. Whenever we do these questions, we want to sketch. And even though we have this single technique, there are a few different scenarios we might run into. So I'm going to deal with them separately in 3 examples. The first type are areas bounded by 2 vertical lines. So here we want to find the area bounded by y equals negative x cubed minus 1, by the x-axis, by the y-axis, and by the line x equals 2. And I'm just going to make a note here that the x-axis is the line with an equation of y equals 0. So we said whenever possible sketch, and that's because we have to determine what is on top and what is on bottom. Now recall, y equals x cubed looks like this. Y equals negative x cubed would look therefore like this, not quite that flat, but it does go momentarily horizontal. Okay, and if we had negative x cubed minus 1, that's going to move it down 1 unit. So if I put that on the grid that I made, or on the axes, it's going to look something like this. And I'm not going to waste a whole lot of time making a beautiful sketch with lots of points. I want the basic shape and the directions. Okay, so that's one of the important curves here. Now we're going to bound it by the x-axis, by the y-axis, and by the vertical line x equals 2. And you can see that the area that shows up here is this that I'm going to give in purple. And that area is some integral. Now we just have to make some decisions. What is on top here? It looks like the green line is what's on top. That would be y equals 0. What's on bottom? That would be what's in black. the curve negative x cubed minus 1. What is the left boundary? Well, that red line is at 0, an x value of 0. And the left and rights are just values. And the right boundary would be 2. So the area is the integral from left to right of top minus bottom. Now that we've cataloged all this stuff, we can just plug it in. Let's see what that gives us. Area is going to be the integral from 0 to 2 of the top, which was 0, minus the bottom, which is negative x cubed minus 1, dx. Okay. Notice that I subtracted the whole curve here. I put it in brackets. X cubed plus 1 dx. And now we just go and evaluate this definite integral. And it's not a particularly tricky one to deal with. So area is going to be, anti-differentiate, we get a quarter x to the 4 plus x from 2 to 0, or 0 to 2 rather. We put in these values. 2 goes in first. Okay, so this whole thing here is big F at 2, the antiderivative at 2, minus big F at 0, or the antiderivative at 0. And we just run it through. 1/4 times 16 is just going to be 4, plus 2, minus 0. Or the area in the end is 6 units squared. Okay, and we can't put these units squared here because we are talking about area. So that's how we're going to deal with it when we actually know the left and right boundaries. In the other two cases, we're going to have to figure out what those left and right boundaries are. So here's our second type, areas bounded by the x-axis. In these cases, we need to find the x-intercepts. And that's pretty straightforward. To find an x-intercept, all you need to do is set y to be 0. Or you can just factor the expression. Okay, so we want to find the area that's enclosed by y equals 3x squared minus 12 and the x-axis. Let's make a quick sketch here. I know that that's a parabola. It opens upward. It's got a y-intercept at negative 12. And it hasn't been shifted left to right, so that's where its vertex is. So there we go. There's our rough sketch of what's going on. We're looking for this area. So once again, it looks like, and this is just coincidental that it's been this case in both of these examples, that the top curve is the x-axis, which is y equals 0. The bottom curve, well, that's the parabola. The left and right boundaries are going to be from here to here. Left and right. And we don't know them. We have to find them. Now the way to do that is just find the x-intercepts of this. So set the curve equal to 0. So 0 equals 3x squared minus 12. That's no big deal for us to solve. If we want to, we could just divide both sides by 3 and call that 0 equals x squared minus 4. Or x squared equals 4. Or x equals plus or minus 2. Okay, or we could have factored it. So obviously, this is the negative 2 right here. And this is the positive 2. Now, if you didn't like that approach, you could have just factored the curve. So it factors to y equals 3x squared minus 4, or 3 by x plus 2x minus 2. Right away, we know what our x-intercepts are. It still gives us a left x-intercept of negative 2 and a right of 2. Aside from that, this is going to look exactly the same as the last example we did. So let's find that area. Area is the integral from the left, which we now know is negative 2, to the right, which is positive 2, of the top curve minus the bottom curve. Let's just pretty that up a little bit so that it's negative 3x squared plus 12. And now we're ready to integrate. And this one works out nicely. It's negative x cubed plus 12x from negative 2 to 2. We're going to put our big F at 2, or antiderivative at 2 in first. So that will be negative 2 cubed plus 12 times 2 minus negative 2 cubed plus 12 times negative 2. Okay, the first bracket's going to be negative 8 plus 24, so that's 16. The next bracket's going to be 8 minus 24, so negative 16. And we finish it off, we get 32 units squared. Okay, but the real important thing about this one is that you found x-intercepts. And every time we factor a polynomial, that's finding x-intercepts. Or if it's a trig function, you might know where those x-intercepts are. They're going to be graphs that you know something about. Last type. We're looking for area bounded by two curves. So maybe there's one that looks like this and one that looks like this. And we want to find this area that's in between them. Well, the whole top and bottom thing is pretty straightforward. But for the left and right, we need to know points of intersection. And finding points of intersection is not that difficult. We just equate the functions. So here we're looking for the area enclosed by y equals x plus 1 and y equals negative x squared plus 1. Let's see what these two things look like. Y equals x plus 1 is a line with a slope of 1. Y equals negative x squared plus 1 is a parabola that opens down with a vertex at 1. Now, I'm not sure exactly where these points of intersections are. I'm just kind of eyeballing it. It kind of looks like they intersect at 0 and something to the negative. But the area that's enclosed is this little piece here. Okay, none of the other areas are bounded on all sides. That's the little portion that's enclosed. So that lets us know a few things. It lets us know that the top curve, apparently, is y equals negative x squared plus 1. That the bottom curve, and I'm calling them all curves, it's a line, is y equals x plus 1. The left and right, those are our points of intersection. Point of intersection. And to find them, it's really quite straightforward. We just equate the two functions. X plus 1 equals negative x squared plus 1. That's going to give us the x values that give the same y on both curves. Let's solve this. I'm going to subtract 1 from both sides. I'm also going to add x squared to both sides. That gives me x squared plus x equals 0, or x by x plus 1 equals 0, with solutions of x equals 0 and x equals negative 1. Oh, so these points of intersection are happening at negative 1 and, as we expected, at 0. So So the left boundary is -1. The right boundary is 0. Once we know that, then finding that area is not going to be difficult. We do our regular stuff. We say area is the integral from the left to the right of the top minus the bottom. And just keep it going. That'll be -x squared minus x. The 1's are going to disappear. And the rest of it is just sort of algebraic drudgery after we integrate. So integrate -1/3 x to the power of 3 minus 1/2 x squared from -1 to 0. Plug them in. So that's -1/3, 0 cubed, minus 1/2, 0 squared. That's our big F, or antiderivative at 0, minus the antiderivative at -1, which is -1/3, -1 cubed, minus 1/2 times -1 squared. This whole thing's going to be 0. This is going to be 1/3 minus 1/2, or 0, minus -1/6. And again, this should give us a positive number in the end. If it doesn't, then something has gone wrong. We get 1/6 units squared. And look at it up there. It does look quite small. That sounds reasonable. The second concept that we're looking at in this video is integration by substitution. So this happens when you have something that looks kind of like it came from the chain rule. Sometimes we need to integrate functions where one component is the derivative of another part. To do this, we can use a technique called integration by substitution. And it's basically the chain rule in reverse. You'll recognize these questions because they look like products or quotients that we don't know quite what to do with. Okay, they look complicated as compared to all of the other ones that we've looked at where you've just had terms separated by pluses or minuses. So the steps to integrate by substitution are: number 1, recognize that the expression has two parts, what I like to call a parent, u, and its derivative, which would be just du by dx. And if you botch which one is which, if you make the wrong call, well, very quickly the problem won't work out for you. So you'll just have to try it the other way around. Then we rewrite the integral in terms of u and du. So we get rid of the x's. And that's going to make the integration really easy. Finally, after we've integrated, we substitute back so that our final expression is in terms of x, so that we don't have u's at the very end. And we should remember that we can always check our integration by differentiating, so you can know whether you've integrated properly. Let's try this one. I've got the integral of x squared plus 3x all to the 4, and then I have a 2x plus 3. Now that looks really suspicious. The 2x plus 3 is the derivative of the x squared plus 3x. So here's how I'm going to set it up. I'll say let u equal x squared plus 3x. That's kind of the parent portion. Du by dx, I'm not looking at the integral at all here. I'm just looking at this statement right here. What is its derivative? Oh, it's 2x plus 3. Lovely. Now I take a look over here. Ooh. We have one of those things, 1 du by dx. So that's very exciting. We can probably work with this. That's step 1. Recognize it, and then figure out what du by dx is. Now I'm going to rewrite in terms of u. So where I saw this, or I'll color code this, where I saw this I can put in this, u. So I've got the integral of u to the fourth. Now, where I see 2x plus 3, I can put in a du by dx. So I have u to the fourth du by dx times dx. In other words, we have u to the fourth du. Now we can integrate. Integrating u to the fourth with respect to u is super easy. Power goes up, flip of the new power goes in front, plus some constant of integration. The last step is to rewrite back in terms of x. So where I have this u, I can put it back to x squared plus 3x. 1/5 x squared plus 3x to the 5. All I did was change that u into this. And then I have a plus c. Now, we did this properly. It worked out. But let's check. Let's check by differentiating what we've got out front. That would give us 1/5 times, the 5 would come down front. And then we'd have x squared plus 3x now to the 4. And the chain rule would say now times by 2x plus 3, the derivative of the inner. That would be x squared plus 3x to the 4 by 2x plus 3, which is what we started with. So we must have done this right. The final answer is this. The check is in red, just to make sure. Let's try another few to get the hang of it. So here you have a 4x minus 2 on the top, a 2x squared minus 2x plus 7 on the bottom. Ask yourself, which one of those is the derivative of which? Is it that 4x minus 2 is the derivative of 2x squared minus 2x plus 7, or vice versa? And I think you can easily say that you know that the parent is going to be this one. And let's just check its derivative. Its derivative would be 4x minus 2. Oh my gosh, we have one of those. That's so exciting. We have 1 du by dx. Yay. So let's rewrite the integral. What's on the bottom here? That's a u. What's on the top? That's a du by dx. And these are all going to work out to be a du at the end, but I'll just show you how we get there. This is like 1 over u times du by dx times dx, or 1 over u du. And the whole u business tells us that we integrate with respect to u, and that we're working in u's here. So now, this is an easy thing for us to integrate. 1 over u, well, 1 over x would turn into ln absolute value of x. Guess what? 1 over u turns into the ln of the absolute value of u, plus c. So again, the integration itself is very straightforward. And then, if we put this back in terms of x, well, look at that very first thing we wrote up here. U is 2x squared minus 2x plus 7. So we're going to state the absolute value of 2x squared minus 2x plus 7 plus c. If we want to check it, checking with logarithmic stuff is easy. Earlier in the course, we had a song for this. Original on the bottom, derivative on the top. Oh, that's what we started with. Things must be good. But this is just the check. Okay? The final answer is this. What's in the box there. Now, so far, we've had exactly 1 du by dx. But you might have some multiple of what du by dx is, and that's fine. So let's take a look over here. We have a slightly more complicated looking one. And sometimes people get confused. They want to do something like this. And I'm just going to preface this with bad. So this isn't the right way to do it. But it's worth a shot. They'd say, oh, I think this is my u. Well, let's follow that thought through. Then the derivative would be everything stays the same, and then you get a 6x, and you'd have to have a u and a du in the original one. Things are just getting really, really messy here. So typically in an exponential question, the u is what is in the exponent. And that will be the case here, and you'll see how it works out. So u is going to be 3x squared minus 4. Now that I've said that, let me just find its derivative. Derivative of 3x squared minus 4 is 6x. And now we take a look over here. Those are glasses. What do we have? We don't have a 6x. We have a negative 12x. Oh dear. We have a 6x times negative 2. So we have negative 2 du by dx. That's fine. We can still work that way. We've got some multiple of the derivative. So let me plug it in. Where we see negative 12x, that's negative 2 du by dx. Where I see this portion here, this is e to the u. And we have a dx. Now that's a horrible order to see things in. Let's rewrite it this way. Or you might just want to skip straight to this. I probably would. The integral of negative 2 e to the u du. Okay, those dx's just divided out. And now we can integrate. And the integration here couldn't be easier. E to the x integrates to e to the x. E to the u integrates to e to the u. And bring back the x's at the very end. Well, u is 3x squared minus 4. This should be our final answer. Let's check it. When we differentiate an exponential, everything stays the same, but we need to be mindful of the chain rule. So we'd have negative 2 e to the 3x squared minus 4 times the derivative of the top, which is 6x. Ooh, look at that. We get negative 12x e to the 3x squared minus 4, which is exactly what we started with in the question. So we must have done it right. Okay, the last thing we'll look at is definite integrals with substitution. We'll use pretty much the same approach, but we need to recall the fundamental theorem of calculus that says the integral from a to b is just the antiderivative at b minus the antiderivative at a. So when we use integration by substitution, we need to change the boundaries, those a's and b's as well, so that they reflect the fact that now we're working in u instead of x. And if we change the boundaries, then we can work entirely in terms of u. Now, you can do it differently and come back to x, but it makes things more difficult. So try it this way, and I think in the long run you'll save yourself some pain. So we have an integral from 0 to 1 here of root x squared plus 3x, and then we have a minus 3 minus 2x. That's really fishy. That minus 3 minus 2x looks a lot like the derivative of x squared plus 3x. So let's set it up. I'm going to say u is x squared plus 3x. Its derivative is 2x plus 3. And I don't have one of those, but I have negative one of those. So we have negative du by dx. Now, here comes the boundary switching part. When x equals 1, u equals something. When x equals 0, u equals something else. And I'm choosing those numbers 0 and 1 because they are the boundaries. So let's see. If I plug the number 1 into this expression here, this is u, I would have 1 squared plus 3 times 1. When x is 1, u is 4. Let's do the same thing for the 0. So when x is 0, what is u? Well, it would be 0 squared plus 3 times 0, or 0. Now let's rewrite the whole integral in terms of u. So the bottom boundary was x equals 0. Now it's going to be u equals 0. The top boundary was x equals 1. Now it's going to be u equals 4. Because when x equals 1, u is 4. Okay, let's keep setting up this integral. We have the square root of x squared plus 3x. Well, that is just u. We have the negative 3 minus 2x. That's negative du by dx. And we have a dx. In other words, we have the integral from where u is 0 to u is 4 of negative root u du. And right away, we know that we don't want to deal with a radical, so let's call that negative u to the half. From here, we can integrate. So power goes up by 1. That's u to the 3 over 2. The flip of the new power goes in front. And we're looking at boundaries of u equals 4 and u equals 0. When we did indefinite integrals, we switched back to x. Here we don't have to. We have everything set up in terms of u. So now I'm going to do this big F at 4 minus big F at 0. And it's all in terms of u. So that will be negative 2/3 times 4 to the 3 over 2 minus negative 2/3 times 0 to the 3 over 2. Or negative 2/3, 4 to the 3 over 2, that's square root of 4, which is 2, cubed is 8, minus 0. When we're done with this whole thing, we should end up with negative 16/3. And just to be sure, I'm going to check with my calculator. There's the original question. Let's just take a look at it. Okay, x squared plus 3x, all square rooted, times negative 3 minus 2x. And I need to put in a dx here. And if we feel a little bit weird about not coming back to the x, let's just make sure that it gives us the same answer. Negative 5.33333, or exactly negative 16/3. So we've done a better job than the calculator. Let's try one last one here. We've got the integral from pi over 4 to pi over 2 of cos over sine. Typically, you want your du on the top. So if you have this kind of setup, let u be what's on the bottom, sine x. Du by dx, that's going to be cos x. Okay, this whole thing is going to end up being really, really tricky if we choose the wrong ones. And what do we have? We have 1 du by dx. Now we could start subbing in, but instead let's check out the boundaries. When x equals pi over 2, u equals, let's see if we remember, what is the sine of pi over 2? It is 1. When x is pi over 4, u is, let's see if we can get this one, the sine of pi over 4. You could call it 1 over root 2. So that's what I'm doing here, sine of pi over 4. 1 over root 2, or root 2 over 2. Doesn't matter. Same value. Okay, so we can begin. This is the integral from where u is, I'll call it root 2 over 2, up to where u is 1. Of cosine, well, that's du by dx, all over sine, that's u, times dx. When we work this through, the dx's are definitely going to be gone. You'll have a du at the end. We can show all those algebraic steps, but it will work out for us. So what will we be left with? We'll have 1 over u du. Now we can integrate. The derivative, or rather the antiderivative of 1 over u is ln of the absolute value of u. And we're doing this from u equals 1 all the way up to u equals root 2 over 2. We plug those in. That'll be ln 1 minus ln of root 2 over 2. Now ln 1 is just 0. So that'll give us negative ln of root 2 over 2. And if you're feeling really fancy, then we can put that in different forms. Or we can get its approximate value, which would be about 0.347. Okay, if I want to check that in my calculator, because it has the fancy buttons, I'll do so and just make sure that it works out. There's the original integral all set up. And look at that. It does give us that same value that we found down below, roughly 0.347. So that covers definite integrals with substitution. We also did indefinite ones and area in the plane. If you look down below, you'll find that there is a review sheet and there are worked solutions. Take care.